Section 5.4 is about indefinite integrals and the net change theorem. So first I'm going to talk about indefinite integrals, but in order to understand them, the first thing you want to recall is section 4.9 and the idea of antiderivatives. Okay, so remember any function capital F, if I take the derivative and I get lowercase f, then we say that capital F is an antiderivative of f. Okay, so the indefinite integral is really just going to be asking us to find the family of all antiderivatives of a given function. So let's do an example. So in this example, notice how I have the integral sign, but there are no numbers on the integral sign. This type of integral is what we call an indefinite integral. And what we're looking for is the family of all antiderivatives of this function f. Okay, so let's take a quick look at this. This is just 10 times 1 over 1 plus x squared. So the antiderivative of this part of the expression is 10 times arctangent. We know that the antiderivative of cosh x is sinh x. And in your textbook, you'll find the formula for the antiderivative of this function, the exponential. And then to make this the most general antiderivative, I'm going to add the constant c. So this part is easy to forget, but remember that we're asking for the set of all antiderivatives, and basically any different constant here would give us a different antiderivative. They're all vertical translations of each other. You can double check by taking the derivative. Okay, this of course would be 0. Let's do another example. Okay. So remember that you can always rewrite these if it helps you. So I could rewrite this one as, okay, you can write the dx as if it's being multiplied by the -2, or as if it's just off to the side like that. The next thing I'm going to do is I'm going to note that I'm going to use a trig identity. So use identities if they help you when you're doing trig. We know that cosecant of x is 1 over sine x. So I can actually rewrite this as okay, and I know that this is just the derivative, this part is just the derivative of cotangent x. But again, I don't want to forget my constant c. So here's my antiderivative, and when I add the constant c, I get the most general antiderivative. And we can check this, right? We just take the derivative of 2 cotangent x plus c, and I get -2 cosecant squared x plus 0, which was my original integrand. Okay, I'm going to do another example from trig because I want to start emphasizing the importance of knowing the trig identities. So we are being asked to find the most general antiderivative of this function. If I look at it as it is right now, this does not look like the derivative of any function I know, so I'm going to try to rewrite it. Now this looks familiar. I remember that if I take, let's see, 1 plus tangent squared x, I get secant squared x. So that implies that tangent squared x is equal to secant squared x minus 1, which is what we have here. So I can rewrite this as 5 tangent squared x over tangent squared x dx. And then this becomes just the integral of 5 dx. So what is the antiderivative of 5? We have 5x, but we need to add our constant c. Okay, so it's important to know your trig identities, especially when you're going into Calc 2 or Math 110b. Let's do one more example that involves absolute value. I'm going to do a simple example because first I just want to illustrate the idea. Okay, I'm also using the variable t just to show you that you don't always have to use x. So this is the integral of the absolute value of 1/2 t minus 1. So the thing to note is that this function in here is just a line. And if I were to graph this line, it would look, on this interval, it would start at -1. So it would start down here. It's equal to 0 when x is 2, and when x is 4, it takes on the value 1. Okay, so the thing to note about this function is, we can already see just by looking at the graph that this interval should be equal to 2, okay, because just by looking at the graph, I can see the area. So let's just use the graph to compute this. Well, I can see that this integral is going to be equal to 0, right? Because I have -1 here and 1 here. And then if I take the absolute value, well, the area should be this area plus this area, so 2. So the key thing to notice is that when on the interval 0 less than or equal to t less than or equal to 2, the function is negative on this interval. In this interval, from the function is positive. Okay, so in general, when you have a function, when you're taking the integral and you have an absolute value, you really want to rewrite your integral to break the interval 0, 4 into sub-intervals where your function is either going to be positive or negative. So for instance, I'm going to break this into the integral where my line is negative. So instead of writing 1/2 t minus 1, I'm going to write the opposite. The absolute value is given by the opposite of this. And then I'm going to add it to the integral from 2 to 4 of 1/2 t minus 1. Because on this interval, the function is positive, and so I don't have to, absolute value is just equal to 1/2 t minus 1. So now I'm just going to write this is 1 minus 1/2 t dt. Okay, now when we integrate this, we get t minus t squared over 4, and we're going to evaluate that from 2 to 0, and then we're going to add t squared over 4 minus t from 4 to 2. So we know this should give us 1, and we end up with 2 minus 2 squared over 4 minus 0 squared over 4. So this is this part. Oh, sorry, I kind of stopped writing here. So let me just recap this. So I broke this into two integrals that should both give me positive numbers. And down here I have, I just flipped the ordering here. And again, I added to this integral. And now I am just evaluating the antiderivative. I'm using fundamental theorem of calculus part 2 here. And I just finished that right here. And then I'm going to add the second part. So I get 4 squared over 4 minus 4, which is just 0, minus 2 squared over 4 minus 2. So that's going to be positive 1. So here I get 0, or 2 minus 1 is 1, right? So this is 1 plus, and then this also gives me 1. So I get 2 for the absolute values, the integral of the absolute value. And if I don't have the absolute value, I get 0 for my integral. And that's what we expected from the picture. So the key thing is that for absolute value integrals, you need to break them up into a collection of integrals. So for example, if this function was displacement, okay, then the integral of the absolute value would give us the distance traveled. And the integral, when I don't have the absolute value, just gives me the displacement. Or sorry, not if this is displacement, if this is the velocity function. Okay, and then if this integral would give me the distance traveled, this would give me the displacement right here. There's just one other thing I want to say. And I want to say something about the net change theorem. And net change theorem is just a way to interpret the fundamental theorem of calculus, part 2. And if all the conditions are satisfied, and you can look at the more detailed presentation in your textbook, then what the fundamental theorem of calculus part 2 is saying is that the integral of f prime of t dt, so the definite integral, is given by f of b minus f of a. Okay, so in other words, if I integrate the rate of change of f, then it gives me the net change in f. So going back to the previous example, so for example, if f represents position or displacement at time t, then f prime is the velocity. So for example, let's suppose I wanted to know how far I had traveled between 2 hours and 5 hours. And this function gave me the miles traveled, or my change in position, my position. So my position at a particular hour. Then if I were to differentiate the velocity, or find the definite integral of the velocity function, this would give me my change in position between 2 hours and 5 hours. Similarly, if let's suppose I have a function p of t, and let's suppose p of t gives me the population at time t, where t is measured in years. Then if I were to compute the definite integral from the year 2000 to the year 2014, this would be the rate of change of the population. at time t, then the definite integral would give me the amount that the population had changed between 2000 and 2014. Okay, so this is just one way to look at the fundamental theorem of calculus part 2. Okay, if you compute the definite integral of a rate of change of a certain quantity, then it gives you the net change in that quantity between those 2 points in time or whatever.